Okay, so let us do a small summary on what we did yesterday. So yesterday we introduced the LU factorization method, and we said that this method will be of high benefit if you want to solve a linear system of equations while varying only the result vector. Okay, so and we have considered two cases if we don't have pivoting. So if you don't have pivoting, we just find LU matrices, and then we perform forward substitution followed by backward substitution to get the result. While if we have to do pivoting, we should create a permutation matrix that can track all pivoting operations. And meanwhile, also with L, each time we do a pivoting in A, we perform also the pivoting for L. And at the end, once we are done with the determination of L, U, and P, so once we do Gauss elimination process for matrix A to get L and U, and any pivoting that will take place will be tracked in P, then we can, for any vector B given, all we have to do is to multiply B by P and say that according to the following relation, we started with this system, we started with AX equals to B. Now, by multiplying the left side by P and the right side by P, then all pivoting that take place will be considered for B also. Okay, so in this case now, I will consider that L times U will be equal to P times A. And now I can proceed with the following relation. LUX equals to PB. So just here I should assess what is this vector, and then I can do forward and backward substitution to get my vector X. Okay. Let us consider an example on this. So we can take the following example. We want to compute PB for B equal to 1, 2, minus 1, 0. So in the last time, they gave us an example where we did pivoting, and we end up with the following matrix P. The permutation matrix P was as follows. Okay. So as you can see, we have ones are not on the diagonal because of pivoting that took place. We had to pivot several times. So now this is the final permutation matrix. We multiply it by vector B that is given. So we update now vector B. Okay, we update vector B. And as you can see here, you have it's a very simple calculation. So 0 times 1 plus 0 times 2 plus 0 times minus 1 plus 1 times 0. So the first element here is 0. The first element, for example, will be obtained by doing the multiplication of fourth row element with the column vector. So 0 times 1 plus 0 times 2, 0, minus 1, 0. So it's minus 1. So you can obtain easily the updated vector B. And once you obtain the updated vector B, then you can solve for your different unknowns. Okay, you can solve for your different unknowns in this equation, the system of equations. Now,
دكتور فينا اسال سؤال عن فوق قبل بليز بالبيفوتنج.
Sure.
دكتور بالماتريكس قال ما غيروا وقت نحن عملنا بالاولى والرابعه ما غيروا ال ما عرفت ليه انا ضلت 100.
قصدك اول مره the first time.
ايه مظبوط.
لانه شربل
مظبوط ضلت هون.
يس قلت لكم اياها ريمارك لاست تايم، لانه انت عملت البيفوتينج قبل ما تعبي ال اول مره. يعني انت وقت قررت تعمل بيفوتينج the first time كانت ال بعد ما فيها شيء، كانت بعد كل هول unknown، صح؟ انت عملت اول pivoting operation، رجعت حددت what are the coefficients f21 f31 و f41. This is why I gave you the remark انه for the first time you do pivoting, okay, يعني لانه كنت بلشت بعدك بالايكويشن بعد ما عبيت L، كانت L بعدها فاضيه. So no need to do any pivoting for L then. لانه انت حددت هول الكوفيشنتس حددتهم من بعد ما عملت البيفوتنج اوبريشن. اوكي، بس من هلا ورايح from now on every time you do pivoting مجبور، لانه صار في elements بال مجبور ساعتها تظبط L accordingly. Just for the first time كانت L بعد ما حطينا فيها شيء. اوكي، then we did updated A before putting any coefficient in L. This is why for the first time we didn't do anything for L, but after we followed after this anytime we did pivoting for the matrix we did the corresponding pivoting for L also. Okay.
دكتور
Yes.
تحت اخر ستيب لما بدنا نلاقي الفاليوز اوف اكس، ما فهمت كيف وصلنا لتحت انه يعرفوا يلاقوا الاكسس.
اوكي لحظه، هون اول شيء فهمت كيف جبنا اليو والبي؟
انه كل وحده لحالها فهمتها والبيفتنج فهمتها انه ليش بنعملها، بس ما فهمت بعدين شو استفدنا بالاخر.
اوكي كثير منيح. طيب جبنا اليو والبي. اوكي، ونحن عندنا this system to solve. اعطونا vector b. اوكي، قالوا لنا solve the system given for this vector b. اوكي، فاول شيء بما انه انت already you did a lot of pivoting يعني الفيكتور b should be updated. اوكي، يعني تنقل هالpivoting اللي صار كمان على vector b. Okay, so what you do, you multiply now p by b, okay, to get the updated vector that you should work with. Okay, once you update the vector, now you can write in you can go back to your equation. Okay, you go back to your equation and you update you update صار عندك full information. Okay, this is L, this is U, and this is your result vector B. Okay, the updated one يعني من بعد B حسميه B prime إذا بدك, because once we did P times B يعني نقلنا كل pivoting, we tracked all pivoting حطيناهم ب B كمان. Okay, now what you will do now, you will solve عادي. يعني شو هي البروسيجر اللي شفناها yesterday? You define vector D as U times X. Okay, so first step will be to find what is D vector. How you find D vector? نعمل forward substitution. شو يعني؟ يعني let us take it here as example. We have this matrix. Okay, this is my U matrix. This is U, this is L. هلا بدي اخذ اول شيء أول step هاكتب L times D equals to, so matrix L times vector D is equal to this vector 0, 1, 2, minus 1. Okay, and now I will find what is the expression for D. Okay, to find it بلش equation by equation. So I will start 1 times D1 اللي هي 0. Sorry, 1 times D1 equals to 0. Okay, so D1 plus عندك 0 D2 0 D3 0 D4. ما أصلا هي this form of the matrix هي اللي خلتك تعمل now forward substitution. So the first equation will be 1 times D1 equals to 0. Okay, now second step. So
بنلاقي كل الديز هيك يعني.
نعم
هيك بيطلع لنا كل الديز 1 2 3 4.
مزبوط. هلا we will proceed to get يعني هلا to get D2 بتنقل على ثاني equation. Okay, ثاني equation هتكون 0.1818 D1 بس D1 is 0 يعني دغري you can replace plus D2 equals to what? شو بتاخد now? تاني element 1. Exactly. You get D2, then you proceed in the same way. You get D3, you get D4. Okay? Once you have D1, D2, D3, D4, you completely define vector D. هلا شو بترجع بتقول؟ بترجع بتقول إنه U times X is equal to D. اوكي ساعتها بترجع الفورورد substitution عادي يعني بس انت بدل ما يكون عندك B you have a vector D. Okay, so now once you get D you write that U times X equal to D. يعني if we do it here صار معنا D1 هناخد this term, this U times X equals to D vector D يعني D1 D2 D3 D4 already عملنا لهم calculation. So now how you will start? You will start to solve for X4. You will do backward now substitution. Why? لأنه هلا الزيروز this is a lower this is an upper triangular matrix while هون عندك lower matrix لأنه هون كانوا elements لتحت. Okay, now elements لفوق. Okay, so now you will do backward substitution. You will start by getting X4. So you write the first equation will be 8.3252 times X4, okay, equals to D4. Now we had already calculated D4. We substitute here. We get X4. Once we get X4, now we are ready to get X3. You move to the third equation اللي حتكون minus 8.5 X3 plus 2.625 X4. You substitute X4 by its value, okay, equals to D3, and D3 also is known. You get X3, and you repeat this to get X2, then X1. Okay?
نفس كتير دكتور.
Okay. Now we will introduce in our problem in this chapter we'll introduce also another factorization technique. If you remember when I talked about LU factorization, I told you it's not the only way to decompose A. Yani you can decompose A. You have several possibilities in decomposing A into a lower and upper matrix. One method to decompose it into a lower times upper matrix is to use the Gauss elimination technique, and from Gauss elimination you can fill U and L. But this is not the only method. We have several ways to divide a matrix into a lower and upper one. One of them is Gauss elimination. We will see now another method that is on as computational time. It will take less time, okay, but it requires some conditions to be done. So if you want to use the Cholesky factorization, we have conditions. The conditions are that the matrix we should deal with should be symmetric and should be positive definite. So we will see what is symmetric and what is positive definite in this in the coming slides. Okay. So now let us introduce what is a symmetric, first a symmetric matrix. So first we say that a matrix is symmetric. First, it can only be a square matrix. What do we mean by square matrix? This means that the number of columns should be equal to the number of rows. So this is the first condition to say that it's a symmetric matrix. And the second condition is that we have matrix A should be equal to its transpose. So last time we defined what is the transpose of a matrix. So any element Cij should be equal to the element Cji of the transpose. So by other terms, we switch rows and columns. Okay, so if I have a matrix, I switch rows to columns, I get the transpose of this matrix. So we should make sure that to have a symmetric matrix, matrix A should be equal to its transpose. So by in other words, entries of A are symmetric about the diagonal. Okay, so it's very easy to verify if a matrix is symmetric or not. Let us take some examples. So you have the following matrices, and you want to determine if it's a symmetric or not. So all you have to do, you draw the diagonal. You don't care for element on the diagonal; they can be any elements. Now you check. Do I have symmetry here? No, 2 is different than 1, so it's not a symmetric matrix. For this matrix here, this is the diagonal. I check, do I have symmetry? Yes, so it's symmetrical. Here, also, as I told you, you don't care for element on the diagonals. They can be different, they can be equal. It doesn't matter. Just you compare the element. You consider this is your mirror line. And since you have symmetry here, so it's a symmetrical matrix. Also here, same thing. Okay. Now here, for example, another example, this is diagonal. Now, if I compare already 2 and -2, it's not symmetrical. They are opposite. They are not equal. So it's not a symmetrical matrix. Now, for this one, I consider this is a diagonal elements. I have symmetry here. I have symmetry here. I have symmetry here. So it's symmetrical. Here, same procedure. I have symmetry. I have symmetry. I have symmetry. So in general, you can also verify if I switch rows and columns, nothing will change. So this is a symmetric matrix. So this is how you verify the first condition. The second condition is to make sure that I have a positive definite matrix. So how I can check this? The condition to say that it's a positive definite matrix is that for any vector x, the transpose of x times matrix A times x should be positive. Okay, so this is the condition. For any vector x, how we can verify this condition? It's very simple. So we will take some examples. Okay. For example, here, we want to demonstrate if this matrix 1, 0, 0, 1 is a positive definite matrix. So what we will do, we will, since the condition is for any vector x, this condition should be satisfied. We will set any vector x with elements a and b. Okay. And we will verify why we used here 2 elements only, because you have your matrix A is characterized by 2 rows, 2 columns. So here, when you do A times X, what was the condition? Okay, so you should have the number of columns of A should be equal to the number of rows of X. Okay, so since A has 2 columns, X should have 2 rows. So vector x is AB. Okay. So now we will demonstrate that whatever is A and B, if we do x, the transpose of x times A times x, we will get a positive result. So to verify that the matrix is positive definite, we should now compute x transpose times A times x. So let us do it step by step. Okay. So whenever I want to do this, pay attention. I should respect the order. So I can start first by doing A times x. Okay. It's very simple. A plus 0b. This is the first element. The second one will be 0a plus b. So the result of this will be just ab. Okay, and now I move to the next step. I multiply this row by this column. So I will get A times A plus B times B. I get A square plus B square. So of course, you know that the summation of 2 squares is always positive. Okay, so I can say now that my matrix is positive definite. Okay. So now we can be sure, okay, that this matrix is positive definite and it's symmetric. So we can use Cholesky factorization with it. Okay. Another example on 3 by 3 matrix. Consider the following 3 by 3 matrix. First, we want to verify that it's symmetric. So this is diagonal, -1, -1, 0, 0, -1, -1. So it's a symmetric matrix. Let us verify that it's positive definite. So we consider any vector x, a, b, c. And now we want to test if it's the definition for positive definite, which is that the transpose of x times matrix A times vector x is higher than 0. So we consider any vector ABC, and we perform again the same operation. We start by doing A times x. So we have 2A minus B plus 0C for the first row. For the second one, we have minus A plus 2B and minus C. So we get the second row. And finally, for the third row element, 0 times A minus B plus 2C. So we are done with it. Okay. Now we continue the procedure. We replace A times X by the following result, and we do X transpose times this result. So it's ABC times the following, which is A times X. So now we proceed. We have A times 2A minus B plus 0C plus B times minus A plus 2B minus C plus C times 0A minus B plus 2C. And now we can try to expand this form and rearrange terms to be sure that it's always positive. So what you can do here, okay, we can decompose our terms. So 2A squared can be written as A squared plus A squared. Okay, you have minus AB is minus 2AB. For 2B squared, we will decompose it into B squared plus B squared. And here you have minus 2BC. And 2C squared will be decomposed into C squared plus C squared. Why we are doing this? To have the factors that can be joined together to form something square. Okay, so these three terms together, A squared minus 2AB plus B squared is A minus B squared. These three together, B squared minus 2BC plus C squared is B minus C squared. So now you end up with the summation of squares. So you can be sure then that this is positive. إلا إذا أكيد the only case it's not is a A, B, C, 0. يعني 0, 0, 0 factor. Okay? So we can say that matrix A is positive definite in this case. Okay, so now once we can make sure that the matrix given is symmetric and positive definite, then Cholesky decomposition will tell us that we can write it in the form of U transpose times U. Okay, and we don't need to do any pivoting. So let us check how to do this. Okay, so our purpose now, once we verified that a matrix is symmetric, positive, definite, we can then find a matrix, okay, any way that A can be written as U times transpose of U, okay? So here we will verify together what will be U transpose times U, which will give us A, okay? So let us do it. So we will consider any upper matrix, upper triangular matrix, and we don't know its components, because here we want to find a general rule to do the factorization of a matrix. So this is a general form for an upper matrix. As we said, an upper matrix will have all elements, including the diagonal and above the diagonal, different than 0. And we will have zeros, فيهم يكون فيهم zeros, okay? But we should have the upper part should all elements should be 0. هلا الباقيين فيهم يكونوا 0 فيهم يكونوا لا. Okay, this is called an upper triangular matrix. So now in this case we want to find what is U to verify that U transpose times U will give us A. Okay, so U transpose here you can get it by just switching rows, and rows will become columns. So U11, U12, U13 will become the first column of U transpose. 0, U22, U23 is the second column. 0, 0, U33 is the third one. And now I will perform the multiplication according to the rules we have learned together. So you have U11 times U11, which is U11 squared, plus 0 plus 0. So the first element should be is U11 squared. Now second element will be, so we continue, we proceed, we do now second row times second column, which will give us U11, U12 plus 0, U22 plus 0. So the second element of my product will be U11, U22. I will proceed in a similar way for all elements. And for example, if I take any element, let's say we want to determine this element. This element is A32. Okay, so it will I will get it from multiplying the elements of row 3 with column 2. So I will get U13, U12 plus U23, U22 plus 0. Okay, so this is my element. You can verify all other terms. Okay, and now what I will do once I write this, I will do comparison between A and this. Okay, because I have the equality. So A is what? Matrix A is A11, A12, A13, etc. Okay, A21, A22, A23. So now I can compare and I can deduce what should be the values of my U's. Okay, so this is A31, A32, and A33. If you do a small comparison now, you will be able to calculate all your elements. Why? Because first you start with this one. Okay, you start with the first column. You have U11 square is equal to A11. So directly you can say that U11 will be equal to radical of A11. Now you know U11, you can proceed to get U12, because now you will say that U11, U12 is equal now to this factor, which is A21. Okay, and already I calculated U11. So you can say now that U12 is A21 over U11. And you will proceed in this way to get all others coefficients, because now from this relation you have U11, U13 equals to A31. So U13 is equal to A31 over U11. Now you can move to the second row. U11 is already calculated, you find U22. Now, once you find U22 by comparison with, you can say that A22 is equal to A12 square plus A22 square. And since U12 is already calculated from this step, you replace it and you get U22. Similarly here, you already got U13 and U12. So you replace them here along with U22, you get U23. Then you move to the third column. Okay, you have by comparison A13 is equal to U11, U13. U11 is already calculated from previous calculations, so you can get U13. Then substituting here U13 and U12 already calculated, in addition to U22, you can get the value of U23. And finally, you compare A33 with this term. You already calculated U13 and U23 from previous steps, so you can determine what is U33. Okay, this might seem long for you, but if you really count the number of operation compared to LU factorization, it is much simpler. Okay, and this is the general rules you can follow to get all coefficients. So U11, as we did together, is radical A11. U12 is A12 over U11. U13 is A13 over U11. Now you can find U22 function of A22 and U12 by doing the comparison as we did. U23 is A23 minus U13, U12 over U22. And you have that U33 is equal to radical A33 minus U13 square minus U23 square. Okay. So now this is حتى you can see here انه no need يعني ال third row بصيروا يتكرروا الاليمنتس يعني نحن already U23 لقيناها من هون so it's not, you don't have it, it's not new anymore here يعني it's already computed before. So بالthird row ما حتعوزوا الا تعملوا comparison of the third term. وبالsecond column كمان you just have to compare these two لانه already يعني you get U22 from this equation and you get already U12 is computed U22 is computed before يعني هيدي الcomparison هون ما حتعوزوها لانه already it's calculated. So in the second row you should have you should do two comparison, just two comparison, because already elements are already calculated previously. يعني just in the first column you should do three comparison. In the second column you only have to do two comparison, and in the third one only one comparison. And already terms are already calculated before, so you can just do verification here if you want. Okay, so at the end you just have to do these computations, 6 computations, and you are done. Compared to LU factorization, the number of operations will be much smaller in this case, but as we said, Cholesky factorization has conditions. You should have symmetric matrix and it should be positive definite. Okay, so now we can try to do an exercise for the following example. So in case we have the following matrix and we want to do factorization, we can use Cholesky factorization because first, if you check, it's a symmetrical matrix. So we have here -6, -6, 12, 12, -9, -9. Now to verify that it's symmetric, okay, we can just prove that if we take any vector x, so let's say here we have we should take x a b c. Okay, look, if in an exam they tell you use Cholesky factorization for the following matrix, يعني أكيد it will satisfy, it is satisfying the rules. So if they don't tell you directly, demonstrate no, it's a this matrix is positive definite and is symmetric, no need to do it. So if they just tell you use Cholesky factorization, this means that it will satisfy the condition. If not, they can ask you verify if this matrix can be factorized using Cholesky factorization. Then you demonstrate that it's symmetric, okay, and you demonstrate that it is. To demonstrate it's symmetric, it's very simple. Just you can just find the matrix A transpose, okay, and you will get the same matrix. So if we do it here, if we put this row, this first row will become the first column. So it's 9, -6, and 12. Okay, and the second row will become the second column. So it's -6, 5, -9. And the third row will become the third column. So it's 12, -9, 21. Okay. So now you can say that I verified first that A is equal to A transpose, so it's symmetric. Second condition, I should verify that it's positive definite. So I should verify that if the formula is تبع X, so I should do first. So if you remember, this is the condition. We already verified this for other matrices. So just try to do it. Try to do x transpose times a times x and verify it's positive. Do it as a practice here. And then once we verify these two conditions, now we can be sure that this matrix can be factorized using Cholesky factorization. Okay, and I repeat, in the exam, if I don't ask you verify that it can be factorized using Cholesky, if I just tell you using Cholesky factorization, determine if you want to do the solution of this case, you don't need to do any verification, okay, unless they ask you to verify. Okay, so now if we want to use Cholesky factorization here, then it's very simple. We just have to apply the following rules. Okay, so now, for example, u11 in this case will be equal to radical of 9, which is equal to 3. U12 will be equal to A12, which is minus 6, over U11, which is 3. Okay, so U12 will be equal to minus 2. U13 is equal to A13, which is 12, over U11, which is 3, so we get 4. Now for U22, it's radical A22 is 5 minus U12 square. We have that U12 is equal to minus 2. So doing minus 2 square, it's 4. So it's radical 1, which is equal to 1. So as you can see here. Now for U23, it's equal to A23, which is minus 9,